No, unfortunately we can't always get what we want, can we? But with maths we can always get what we need. So today we're going to be looking at stationary points. So if you'd like to have a little look at this graphic and make a copy of it, we're going to look at a table and take that through in a moment. Okay, there's a table on page 273 of the textbook that looks like this. It's about stationary points. Remember, a stationary point is when the gradient is equal to 0. So at that point, x and y is not changing relative to each other just at that moment. Now we're going to have a little look at what these different things mean here. Local maximums, local minimums, and points of inflection. So here's the graphic that was up a minute ago, and I've drawn it again because it's very important. The first one here where it says local maximum, and then here it says the function of x minus h, and h is just meant to be a small value. So if you took a small amount off x, what would it give you? So if that went to there, what would you have there? That gradient is positive at the moment. That's why that's there. And then if you go a little bit further, it becomes negative. So when you have a 0 gradient, that just before it got there was positive and it's just going to become negative, that's a local maximum because it's at the highest point that the curve will reach at that point. And when it's right on that value of x, we've got a gradient of 0. Now the next one, local minimum, that's what we've got here. So what's happening? Well, just before, if I take a tiny bit off my value of x, I'm going to have a negative gradient. And if I'm going to have a tiny bit more on it, I'm going to have a positive. So that is a local minimum. So we've got negative just before and positive just afterwards. So that's a local minimum. And then the other thing we need to know about is a point of inflection. So a point of inflection, this one here, just before we get there it's negative, and just afterwards it's negative. And the other way that a point of inflection could happen is if we had a different curve coming up and doing that. Before it was positive and afterwards it's positive. So the point is that it doesn't change and go the other way, it stays with whatever it was. So it's either negative and negative or positive and positive. And that's always a 0 there either way. Right, okay, so once you've got that copied down, we'll be ready to have a look at our 2 examples for today. Right, the first part of this question, find the coordinates of the stationary point on the curve y equals x to the power 4 minus 32x, is no different to what we've done already. You just need to differentiate. So have a go at, pause the video, have a go at doing that, and then we'll go through it. So you should have dy over dx is equal to 4x cubed take 32. So that's the gradient function, and we need to know what point x is equal to that. So we need when that is equal to 0, then it'll be a stationary point. So if I add 32 to both sides, I get 4x cubed equals 32. And then dividing by 4 would give us x cubed is 8. And then the cube root of 8 is 2. So x equals 2. Now we know x equals 2, but what's our y value? So our y value, we need to go back into our original equation and say when x equals 2, y will equal 2 to the power of 4 minus 32 times 2, and 2 to the power 4 is 16, so we're doing 16 take away 64, which is negative 48. So we can then go up there and put that in as our y value. Right, here's the second part of the question where something new comes in. It's a bit of a mouthful, but it actually tells you what to do. So you might want to have a little go at this before I talk it through. So why don't you pause the video and do that. Great, so by considering points on either side of the stationary point, well, first of all, what is the stationary point? It is 2, negative 48. So what we need to think about is the curve going up or down either side? And you can give any point either side, but we tend to go for something really quite close to it. So if you say if x equals 1.9, y is going to equal, and then we will do 1.9 to the power of 4 take 32 times 1.9, and that should give us negative 4.56. And then if we go for if x is 2.1, we would do y is 2.1 to the power of 4 take 32 times 2.1, put that into your calculator, and we should get 5.04, which is positive, isn't it? So now we need to think about what's happening. When it's at 1.9, it's negative. When it's at 2, it's 0. And when it's at 2.1, the gradient is positive. So that's negative, that's 0, and that's positive, which means it's at the bottom, so that makes it a local minimum. The reason it's called local, by the way, is because at other points in the graph it may well go below that. Okay, so that's that one. Right, I'd like you to make some notes on this. Most of the time you can use the second derivative, what we were doing yesterday, to find what kind of stationary point we have. Now this is where it gets confusing. If a function is stationary, a function x is stationary when x equals a, so that means we can put in, once we know the stationary point, if we substitute the value that is the x coordinate into your second derivative, if you get more than 0, the point is a, and this is counterintuitive, it's a minimum if it's more than 0. So if you get a positive answer, that means it's the minimum point, because it's always going to get bigger afterwards, either side of it. And if the answer you get from the second derivative is less than 0, the point you've got is actually a maximum, because everything else is going to give you something that's negative. And then the reason we said at the very beginning it was only most of the time we could use this is if you end up getting exactly 0, then you know that you could have a local minimum, a local maximum, or point of inflection. Now all this bit that I've written here I will put up again as the bit from the book on page 274 so that you can note it down. Okay, next example, first part, find the coordinates of the stationary points for y equals 2x cubed minus 15x squared plus 24x plus 6. Pause the video, give it a go. Alright, so what you should then have is you find the derivative first of all. which should give you 6x squared minus 30x plus 24. Now we need to know when this would be 0. So if we say that's equal to 0, I can see 6 goes into all of those, so I can make my life easier. If I say it's x squared minus 50 minus 5x plus 4 equals 0. Now, to solve that, we need to factorize. So multiplying to make 4, but adding to make minus 5. So we have got a negative times a negative, and it's 4 and 1. So x equals 1 or x equals 4. So we're going to have 2 points here, 1 something and 4 something. And we need to substitute back into the original equation. So when y equals 2 times 1 cubed minus 15 times 1 squared plus 24 plus 6, we get 17. And then when x is 4, we get negative 10. So our 2 points are 1, 17 and 4, negative 10. Here's the second part. So we've got to differentiate again and then use that to find the nature of the stationary points. Pause the video and give it a go. So we're going to differentiate again. So here's our original differential from the first part. 2 6s are 12x minus 30. And then to find the nature of the stationary points, we need to put the x value that we had in there. So when x equals 1, 12x minus 30 is going to be 12 minus 30 is negative 18. Because it's negative, that means it is a local maximum, so we can say that 117 is a local maximum. And then we do the same thing again when x equals 4. 12 times 4 is, take 30, is actually plus 18, so 4 negative 10 is a local minimum. And it would always be a good idea to get your calculator and graph it, just so you could quickly check that that is the case. Now there is one more example, but I'm not going to do it for you right now. What I'd like you to do is have a go at exercise 12i, and I will post on my working through for the third example. Always feel free to have a look at it in the textbook if you like anyway. Exercise 12i, page 276, and if you could have a go at questions 1, 3, 5, 6 and 7. And don't worry if things get a bit tricky, do please get in touch and I will help you out on that. Okay, thank you very much. Goodbye everyone, I hope you enjoy that.